Why does AI give a different response each time? Can AI be deterministic? And is it a good idea? What do terms like temperature, truncation, sampling, Softmax, and Logits mean? Is AI just a stochastic machine for predicting the next word?
You will learn this and more in today's episode. Without further ado, let's begin. Just please tell me if you want to start with important theory or invaluable practice.
We definitely should start with practice.
As you wish. So we are starting with Google's AI Studio, and we'll be working with their Gemini 2.5 flashlight model. The Studio offers a fantastic feature for comparing two responses, whether you're using the same model with identical settings or two different ones. In our case, we're looking at the same model with the exact same settings. I'm asking now about a simple thing, about favorite animals. It's probably clear that you shouldn't expect a different answer every time. But is that really the case?
The lists start similarly, but the endings are completely different.
Exactly. But let's do another experiment. I'll adjust the model settings a bit and set the temperature and the TOPP parameter to 0.
What do these parameters mean?
I'll cover this in detail during the theoretical section. For now, let's concentrate on how it will impact the model's responses.
Okay, let's see how it works in practice.
I still need to remove the current conversation to make sure the context is cleared out. It's really important that both instances start under the same conditions.
I see that the question is the same.
Yes, but for us the most important thing is to compare both sides. See, this time we've got exactly the same answer on each side.
Word for word the same.
Yes, and what does that indicate?
That with these settings, we will always get the same answer for the same prompt?
Let's confirm it experimentally once again. This time, I will ask a different question that will result in the generation of a longer text. I'm asking Gemini to generate any story in 10 sentences. It may choose any topic.
It chose the story about the old lighthouse keeper Elias. In fact, both are exactly the same, word for word.
Everything makes sense, but let's check if this isn't specific to Gemini. Grok provides access to various models for free testing, including the open source OSS from OpenAI. Let's test exactly the same prompt.
The story begins with exactly the same words. And the main character is the old lighthouse keeper Elias. Is that normal?
I am also very surprised. Maybe someone from the audience can explain this phenomenon, that out of all the stories in the world, both models from different companies chose exactly the same Elias. Write what you think about it in the comment.
Interesting. By the way, I see that the temperature is set to 0.
Yes, I want to test if at a temperature set to 0, the responses will be exactly the same.
Yes, it's exactly the same story. Can we then assume that if we set the parameters correctly, large language models become deterministic?
First of all, not correctly, but specifically. And secondly, both yes and no.
What do you mean?
When the temperature is set to 0, the model will consistently give the same response to an identical prompt, at least until either the model version or the system prompt changes. So from a technical point of view, a neural network is deterministic. But from a practical point of view, not entirely.
Again, what do you mean?
I'll demonstrate this with an example. I'll make a slight change to this prompt. I'm assuming that the period at the end of the sentence doesn't matter to you. So, these are essentially two identical prompts, right?
It can be said so.
And look, one small dot and the story changed. It begins the same way, but the ending is different.
Indeed, but it's just a minor change.
Do you think so? It can completely change the meaning. I'm changing 10 from numerals to the word.
Okay, still a small change. The meaning remains the same.
You see, the story has completely changed, although the main character has remained the same.
So, setting the temperature to 0 does make the model's responses deterministic. But in practice, it doesn't actually ensure stable answers, does it?
It doesn't, but it's important to understand how these parameters work, because they can impact the creativity and potential hallucinations of models. That's why I want to explain how it all works, so you can adjust the settings to suit your needs.
Okay, So, we are starting the theory.
Hold on a second. First, we're going to do an experiment. Later, we'll compare it with the theory.
Okay.
In this program, we asked the open source model Gema from Google about its favorite animal 100 times, and then we compile statistics from its responses.
In the code, I see that the temperature parameter is set to 1.0.
Yes, this is a completely standard setting.
I've noticed that the most common response is a dog.
It looks that way. But let's wait until the experiment is over to see what the results can tell us.
We have the results. The dog, 72 times.
Actually, 73 if we add the one with the emoji.
I understand that you will change the temperature now to make some comparison.
Yes, I'm changing the temperature to 1.5, which should already make a noticeable difference.
I have the impression that it started slight hallucinations.
Yes, we have answers that contain more than one word, but the variety is somewhat greater. Bigger risk of hallucinations, but on the other hand, greater imagination.
Yes, noticeably, but quality might already be a problem.
I fully agree, but it's a small and older model, what needs to be taken into account. Indeed, the results are not the best. For example, the word doggons probably doesn't exist.
It definitely doesn't exist. So, what should we do next?
Let's gather all the data and create a simple chart to visualize it. Since we ran the test 100 times, we have a straightforward and fairly accurate estimation of the probability.
I see that the probability distribution has clearly changed. The most likely option has lost a lot, while all the others have gained, and the least likely ones have gained the most. So we can say the distribution has flattened.
We could say so.
Could you break this down from a theoretical angle?
I can give it a shot, but there's a lot of theory involved, so I can't cover the absolute basics here. If you're curious about the fundamentals of neural networks and want to understand why they are deterministic, make sure to check out the video where I explain the concept of the number of parameters in LLM. You'll get the basics there.
And could you at least tell a very, very short version of the story?
In simple terms, a neural network is a mathematical structure that processes input data. It carries out calculations, mainly multiplying and adding specific weights, and then produces a result in the output layer. Because these weights are set, the output for a given input is always the same. To put it simply, large language models are essentially neural networks, so they are in fact deterministic. In this episode, we will not delve deeply into how LLMs work, but we will discuss in detail all the elements that cause the final result to vary each time. Let's assume that LLM is a black box for us. It receives some input. Then LLM processes it, and as a result, predicts the next word, or more specifically a token, which can be part of a word. Then this token extends the context, returning to the input, and processing occurs again, allowing us to receive another token. This continues until the model decides it's time for a special token ending the conversation.
A token is a piece of text, isn't it?
It could be anything, a part of an image, a snippet of audio, or a word, like in our case. Let me start by showing you a tokenizer. This is the mechanism that allows converting text into tokens. This one is for OpenAI models.
So you enter text and you get something called tokens, right?
You could say that. My text is divided into tokens, because for us tokens are exactly pieces of text.
Well, I see that we have 4 tokens which have been nicely colored.
That's correct. However, for further processing, it's worth noting that each of the tokens has its own identifier. So we have 4 identifiers. For example, word my translates to 5444. Each model thus has its own set of tokens it operates with, and each of them might use a different dictionary, so a different tokenizer might be needed.
Okay, it looks quite simple. We have 2 representations of the token, as a piece of text or as an index of the dictionary.
Exactly. Let's now summarize how input processing works. So, our input is processed by a tokenizer, allowing us to obtain token IDs, which will be further processed by our black box. What we receive at the output is also a token identifier. which can be directed to the proper place for further processing.
All right. And how does that relate to embedding vectors? Because I've heard that LLMs operate rather on semantic vectors than on identifiers.
Yes, it's true. Artificial intelligence knows the meaning of words through vectors, whose direction determines not only the meaning, but also relationships between words. But that's probably a topic for another episode. For our considerations, let's simply assume that our black box needs these vectors.
How to calculate them?
The vector can be obtained directly from the embedding matrix. The matrix is a part of each model, calculated during its training process. The number of rows in the matrix is equal to the dimension of the embedding vector's space. The number of columns depends on the size of the token dictionary, and it's often tens or even hundreds of thousands of entries.
So it's rather a big matrix.
Yes, especially since the dimension of embeddings is usually also counted in thousands.
I guess that to obtain a vector for a given token, I just need to select the appropriate column.
Yes, column 5444 for the token my. So we have one token with three representations: semantic vector, token ID, and the corresponding chunk of text.
So all three are the same, just needed at different stages of processing.
Correct. Let's update our diagram with the black box. Once we have the token ID, we look it up in the embedding matrix to find the right column. This gives us the embedding vector, which is then used in the context for our large language model.
Okay, but how does this relate to AI determinism? Why are we bringing all this up?
Understanding the basics of input and how it works will help us explore how output is generated, where nondeterminism comes into play.
And what do we get as output from our black box? A vector?
Yes, a vector.
So, do we find this vector in the embedding matrix?
It's not that simple, because this is not a vector from our dictionary. But let's return for a moment to our embedding matrix to explain this.
Yes. This was the matrix binding embedding vectors with token indices.
Yes. However, there is also another matrix with opposite dimensions. It is called the unembedding matrix, decoder matrix, or output projection matrix.
Is this a mirror reflection of the embedding matrix?
In mathematics, swapping rows with columns in matrices is known as transposition. Now, if you're using what we call weight tying in the learning process, then matrix U becomes a transposed version of matrix E. This is commonly seen, but it's not a requirement. It's a model design decision.
Okay. So what do we do next with this matrix U?
So we've got two things here. First, there's the unembedding matrix, which is a fixed part of the model. And second, there's the output from our language model, the final hidden state vector, which the model generated based on the context so far. Let's label it as H. Now we can perform matrix vector multiplication, which gives us a vector of Logits. Let's call this vector Z. Notice that Z has the same number of dimensions as the number of unique tokens in the vocabulary.
Does this vector have anything in common with the probabilities for individual tokens?
A bit like that, but for sure it's not probability because it doesn't sum up to 1. And how would you understand the elements of the vector?
I believe that the higher the number, the more likely it is that this is the token that the language model wants to show us.
I think that is quite a good intuition. Mathematically, each logit is the dot product of the hidden vector and the embedding of a given token. So we can think of it as a measure of the directional similarity between the hidden vector and the specific embedding. This implies a potentially greater semantic closeness.
So we choose the highest number and we have the next token?
Potentially yes, but not so quickly. Let's see what Softmax can give us.
Softmax?
Yes, we want to transform the vector Z into a probability.
So a kind of normalization, right?
We transform vector Z by applying the exponential function to each of its components. The resulting vector X preserves the same order as Z. Next, each element of the vector is divided by the sum of all the elements. This way, we obtain a normalized vector P. Since its elements sum up to 1, we can treat it as a probability distribution for the tokens in our vocabulary. This function is called Softmax.
Can we see this in a more practical example?
Let's try. Imagine vector z, which is our Logits in 7-dimensional space. So we have a dictionary consisting of only 7 tokens. Additionally, they are already sorted from largest to smallest. Of course, we still know which token corresponds to which index. Let's now consider what softmax will look like for this vector. I can apply the exponential function to each component. By the way, I'll be rounding off all the results. The sum of the elements of vector x is approximately 10. The next step is to divide the elements of matrix x by their sum, which gives us vector p. The sum of the elements in this vector is 1, so we can treat it as a probability vector.
So we have a vector that assigns some probability to each token in our dictionary, right?
Exactly.
So now, just like with classification, we pick the option with the highest probability. Am I right?
Well, it depends from our strategy. If we select the token with the highest probability, we are applying greedy search. This is a deterministic decoding strategy.
So probably such a model will not be very creative.
You could say that. And that is why an operation called sampling is usually performed.
Sampling?
Yes, in the simplest version, we can draw any token from the entire vocabulary according to the calculated probabilities. This is then called random sampling.
But then tokens completely unrelated to the context may be drawn, even if this is unlikely.
That's why we often use a technique called truncation, along with other sampling methods. For instance, we might sample a token from the list of the top k most probable candidates. This approach is known as top k sampling.
This approach might work better.
Sure, but it has its downsides too. If we have a distribution with one really dominant token, there's a chance we might draw something totally unrelated to the context.
So, what is the solution to this problem?
Most of the leading LLMs today use the nucleus sampling technique.
How does it work?
We start summing probabilities from the top. Once the cumulative probability reaches the threshold defined by the top p parameter, we truncate the distribution and discard the remaining low probability tokens. Finally, we sample the next token only from this reduced set.
Oh, this is the top p parameter we set when building a query for the LLM.
Yes, apart from temperature, this is the main factor that influences how non-deterministic the model can be.
And how exactly does the temperature parameter work?
To get a better grasp of this, let's return to the softmax function. Now, performing the first operation, let's divide the elements of vector z by parameter t. For t equal to 1, which is the standard temperature, absolutely nothing changes in these calculations. The probability for a dog is 73%, and for a bear, it is 1%. But let's change t to 1.5 now.
The dog's probability is now only 54%, while the bear's has increased to 3%. This shows that the probability distribution has flattened out.
Exactly. Now, less matching tokens are more likely.
So, a greater risk of hallucinations, but on the other hand, we see it as better imagination, right?
You could say that. Let's see what happens when we change t to 5.
Here, I already expect huge hallucinations.
Therefore, the maximum value of this parameter is usually 2. Let's see what the situation looks like for t equal to half.
Here, drawing something other than a dog is very unlikely. So, a lower temperature gives more repeatable results.
That's right.
But am I the only one with general doubts about this whole sampling of the next token? The selected token doesn't necessarily have to be what came out of the neural network. It's like putting words in its mouth that it didn't necessarily want to say.
You've got a beautiful intuition about what you're saying. The reality is, though, this method has been put to the test in real-world situations, and it just works well.
I believe the model needs a lot of flexibility, especially since we're always adding new, quite random words to the context. Maybe that's where its creativity stems from.
I don't know. Maybe. Let's focus on the technical aspects and summarize what we know so far about the surroundings of our black box. We have already discussed the input. Now let's focus on the output. Black box provided us with the hidden vector, which, when multiplied by the unembedding matrix, gave us the Logits vector. Next, we applied the softmax function to get a probability vector, which, through the sampling process, provided us with the output token ID. This token ID can then be fed back into the input thanks to the embedding matrix. And the process repeats.
I would say that this is quite complex, but in the end, every step is clear.
Yes, we tried to explain it clearly, but I understand that having some background in algebra and statistics can definitely help with comprehension. Still, I hope it was clear for everyone. Keep in mind that we made some generalizations, and each large language model might implement these elements differently with its own optimizations. Despite that, I hope we conveyed the core concept accurately.
We put a lot of work into recording this episode, so please give it a like and subscribe to the channel.
May the mechanisms of artificial intelligence never be a mystery to you. See you next time.